The best vacuum that can be achieved in the laboratory has pressure 10 to the power minus 13 Pascal. The number of gas molecules present in 1 cubic centimeter of such a vacuum at 300 Kelvin is, take Boltzmann constant 4/3 into 10 to the power minus 23 joules per Kelvin. I will use PV equals nRT for the corresponding gas sample. Pressure. Then I will substitute number of moles is number of molecules divided by Avogadro constant into RT. Now we know that ROL is the Boltzmann constant, it is K. Then we can substitute PV equals NKT. K means Boltzmann constant. Now I will substitute values. Pressure 10 to the power minus 13. Volume 1 cubic centimeter, 1 into 10 to the power minus 6. We have to convert cubic centimeters to cubic meters. And we have to find the number of molecules. K is Boltzmann constant. We can substitute value given as 4/3 into 10 to the power minus 23. T is the absolute temperature. It is 300 Kelvin. Now we can simplify. 3 divided by 3, 100. 10 to the power minus 23 into 10, 100. 10 to the power minus 21. Then 10 to the power 13 plus 6, 19. We can cancel out 10 to the power minus 2 in this side. We can bring 10 to the power minus 2 and 4 to the left hand side. Then n equals 10 to the power minus 2 means 100. We can get it to the right hand side as 10 to the power 2. It is 100. Divide by 4. 25. Then answer is 4. In order to double the root mean squared speed of an ideal gas, the factor by which the absolute temperature of the gas to be increased is root mean squared velocity. It means the square root of c square bar, directly proportional to square root of temperature. Now we have to double this whole value. Then we have to get 4 times of temperature because of root 4 is 2. Root mean squared velocity is this whole value with the square root. Therefore, term of square root of c square by should be doubled. But temperature should be 4 times because of we have to consider only temperature, not root temperature. Then answer is 3. A fish in a lake releases an air bubble of volume 2.5 into 10 to the power minus 7 cubic meters. This bubble subsequently releases the volume of 10 to the power minus 6 cubic meters air into the atmosphere. If the atmospheric pressure is 10 to the power 5 Pascal and the density of water 1000, depth of the position of the fish is. Now there is no change of temperature. Then we can use Boyle's law. P1 V1 equals P2 V2. Pressure at corresponding depth, atmospheric pressure plus H rho G. Volume is given as 2.5 into 10 to the power minus 7. Pressure at the atmosphere 10 to the power 5. Volume is given as 10 to the power minus 6. Then we have to substitute rho and g. Rho is density of water, it is given as 1000. G is gravitational acceleration. And we can find the value of h. I will cancel out 10 to the power minus 7 and 10 to the power minus 6. Then 10 to the power minus 1. 10 to the power 5 plus H value. We have to find H value. Density 1000, G10. It should be equal to 10 to the power 5. When bring 10 to the power minus 1 to the right hand, we have to put 10 to the power plus 1. Then 10 to the power 6 divide by 2.5. 10 to the power 5 plus 10 to the power 4h equals 10 to the power 6 divided by 2.5. We can cancel out 10 to the power 5. Then 10 to the power 4. Then this value is 10. 10 to the power 2. 10 to the power 2 means 100. 100 divided by 2.5. 40. We can subtract 10. Then H equals 40 minus 10. It is 30 meters. In an automobile engine, the gas, the mixture of air and petrol in the cylinder is compressed to 1/9 of its original volume. The initial pressure is 1 atm and the initial temperature is 27 degrees Celsius. The pressure after compression is 21 atm. The temperature of the compressed gas is. Assume that gas behaves an ideal gas. Pressure, volume and temperature all are changing. Then we can get P1 V1 over T1 equals to P2 V2 over T2. Initial pressure 1 atm. I will consider initial volume as V divided by initial temperature 27 degrees Celsius. It means 300 Kelvin. You have to add 273 to convert Celsius to Kelvin. Pressure at second situation 21 atm. Now I have used atm for the unit as the unit of pressure, but it is not compulsory to convert the unit because of atm is cancelling out. Now volume is V over 9. It is 1/9 of initial value. We have to find final temperature T2. Then we can cancel out V and V. 9 divided by 3 3, 21 divided by 3 7, 3 divided by 3 100. T2 equals 7 into 100 700. Now it is Kelvin value. We have to convert it to Celsius because of all values in answers are given in Celsius. Then we can subtract 273 to convert Kelvin to Celsius. 10 minus 3 7, 9 minus 7 2, 6 minus 4 2 4, 427 degrees. Then answer is 3. Number 5. A vessel containing an ideal gas at 27 degrees Celsius. If the temperature of the gas increases to 127 degrees, the ratio mean kinetic energy of gas atoms at 127 divided by mean kinetic energy of gas atoms at 27 degrees. We know that according to Boltzmann law, kinetic energy directly proportional to absolute temperature. Therefore, when finding ratio between kinetic energy, we can get the ratio between absolute temperature. 127 means 400 Kelvin. We have to divide by 27 degrees Celsius means 300 Kelvin. Then ratio is 4 to 3. Answer is 3. The atoms of an ideal gas have a certain mean kinetic energy at 10 degrees Celsius. Their mean kinetic energy will be twice. We have to find the temperature. We can observe twice of the initial mean kinetic energy. Again, we have to use same relationship. Kinetic energy directly proportional to absolute temperature. Then initial kinetic energy, I will consider it as E, directly proportional to initial temperature is 10 degrees Celsius, we have to convert it to Kelvin, 283. Then we have to get 2 times of kinetic energy. We have to find the corresponding temperature. I will consider temperature as T. Then we can divide 2 equations. E is cancelling out. 1 over 2 equals 283 divided by T. Then we can subject T. T equals 283 multiplied by 2. 2 into 3, 6. 2 into 8, 16. 1 remaining. 2 into 2, 4 plus 1, 5. It is in Kelvin. But again we have to find the Celsius value. To find the Celsius value, we have to subtract 273. 6 minus 3, 3. 16 minus 3, 7, 9. 4 minus 2, 2. 293 Celsius. Then answer is 3. A student performed an experiment to verify Boyle's law using a constant mass m0 of an ideal gas at the room temperature 27 degrees and obtain the graphs given in figure. Here P is pressure, V is volume of the gas. He then removed a certain amount of gas from the volume V and repeated the experiment at temperature 100 degrees above the room temperature. It means new temperature should be 127 degrees. If the new graph he obtained has the same gradient, the graph shown in the figure, the mass of the gas that he removed. Now we can get PV equals nRT, PV equals number of moles equals to mass over mole mass into RT. Then we can get P equals to M R over M MRT over M into 1 over V. Now it is in the form Y equals Mx. Then we can compare gradient. When comparing gradient, we can get initial mass m0, it is given in the question. R constant, initial temperature 27 degrees, it means 300 Kelvin, divided by molar mass M, it is constant for the corresponding gas. It should be equal to, for the final condition, m0 minus M. We have to find this removed mass. Capital R constant, it is gas constant, universal gas constant, temperature 400, divided by molar mass. Then we can cancel out M and M, 2 zeros, R and R. Then we can find simple M value. 3m0 equals to 4m0 minus 4m. 4m0 minus 3m0 m0 equals 4m, then m equals m0 divided by 4. Then 1/4 of initial mass has been removed. Answer is 3. The volume V of mixture of ideal gases contains Na moles of gas A and Nb. Nb is less than Na. It is given in the question. Moles of gas B at a constant temperature. The variation of partial pressure PA, PB of gas A and B respectively and overall pressure PM of mixture with 1 over V at the above constant temperature is best represented in. Now that pressure directly proportional to number of moles. Therefore, when increasing number of moles, we can obtain a high pressure. And the graph between pressure and 1 over V should be a graph like this. It should pass 273 minus 273 absolute 0. No, it is 1 over V, but it should be with, I will derive the equation. PV equals nRT. Then P equals nRT over V. No, it is in the form Y equals mx plus C. Y equals, gradient is this one, mx. It is in the form Y equals mx. Therefore, it should be like this. Number of molecules of A is the greatest value, greater than B. Therefore, PA curve PB curve should be like this, and total pressure is greater than both values. Therefore, total pressure PM should be like this. But there is no an answer with Y equals mx type, because of we know that it is partial pressure, PA and Pn. When considering partial pressure, it is not the total pressure. There is an initial pressure for the corresponding gas. Therefore, it should be past a point like this. Then we can get third one as the correct answer. But if there is a graph such that Y equals mx, passing origin graph, we have to get that answer, but most suitable answer is third one in given answer. Hydrogen gas in a container is maintained at a standard temperature 300 Kelvin and pressure 1 into 10 to the power 5 Newton per square meter. If the root mean squared speed of hydrogen molecule is 2 kilometers per second, what is the density of hydrogen in the container? We can use the relationship between pressure and density. P equals 1 over 3 rho C square bar. Now, pressure 1 into 10 to the power 5, 1 over 3. Density, we have to find the density, root mean squared velocity, not root mean squared velocity, it is mean squared velocity, not root. Therefore, we have to substitute given velocity with the square term. It means 2 kilometers per second, 2000 meters per second squared. Now we can simplify to find the value of rho. 3 into 10 to the power 5 divided by 2 squared 4 into 10 to the power 6. 3 divided by 4, 0.75 divided by 10, 0.075 kilograms per cubic meter. Then we can get second one is the correct answer. Number 10. The mean kinetic energy of an ideal gas depends on its absolute temperature. We know that kinetic energy is depending on absolute temperature. It is directly proportional to absolute temperature. Then answer is 4 for the question.